Okay, so calculus integrals part 2, day number 4. This is on proof of convergence. What I want to start with, first of all, is what we talked about a little bit yesterday. And we may or may not have talked about it in the generic case, but this is called the P series, right? For this P, this exponent right here. If I have an integral, or the area of an improper integral, from some constant, we'll call it a, which is greater than 0, off to infinity, or that's a negative a to negative infinity. That will be, and of course c here will be some kind of real number, right? Just a constant as well. That will be convergent if what's true about p. If p is, yesterday we talked about it, right? We said, what did we say about this integral from 1 to infinity of 1 over x? Was that convergent or divergent? Divergence. And then the moment we did this to it and made that 1 over x squared, that became convergent. Right? Because when I take the integral of this, I get natural log of x. Well, and if I send that from 1 to infinity, what's the natural log of infinity? It's infinity. So it doesn't exist. But once I change that exponent to anything that's greater than 1, it could be 1.1, it is now convergent. So it's convergent if p is greater than 1. It's divergent if p is less than or equal to 1. Okay, and that's going to help us today. It's going to be your best friend, because you're going to compare other integrals to p series integrals. Okay, so here we go. What we want to do, right, is an example like the following. There's a lot going on this page, but basically, if we have an integral, an improper integral, and we're not sure how to integrate it, if I have a function that's always greater than that, and that function converges, then it would force the lower function to also converge. Do you agree? So in this instance here, I don't like the graphic that's placed here, so I'm just going to draw something else. Let's say I have the integral of g of x from 1 to infinity dx, and it's just ugly, and I don't want to integrate that because A, I can't, and B, it's going to be real nasty. And let's say it looks like this, right? I don't know what that function is, but if I can show that this is less than or equal to some p series function, let's say 1 over x squared dx, for all values, right, off to infinity, then I can show that that red graph must converge because it will be less than for all values. You with me? So if I can show that g of x is less than or equal to some p series function where p is greater than 1, I can prove that the integral exists, right? That the area under that curve is convergent. Okay, the alternative is also true. Let's say I'm not sure on h of x. Here's h of x. I'm not quite sure. Well, how could I prove that h of x is divergent then? What would have to be true of, let's call this t of x? If I could prove that t of x was divergent, I could show that h of x is also divergent. Say again? How or what related? I'm about to show you. I'm just giving you a visual sense of what's going to happen here. So if h of x is always greater, the output of h of x is always greater than t of x, and t of x diverges, then h of x also must diverge. So let's see if I can connect that with an example here. So does e to the negative x squared dx converge? I don't know. Right? Do you? It does? Does it? I don't know. Well, let's look at e to the negative x, because I don't want to integrate e to the negative x squared, and I don't think you do either, because u sub's not going to work. Integration by parts is going to be like just sinfully nasty. U sub won't work because what would you set u as? Negative x squared. Then you'd get negative 2x dx, and I don't see a negative 2x dx anywhere. Not to mention, some of you did this on your quiz. You took out of your integral A variable. You can never pull out of your integral a variable. You can only pull out constants, right? So some of you on number 3 on your quiz put arctangent of square root of 7. False. You can't pull out an x on the outside of your integral. Okay? You can only pull constants out. So let's do this. Would you agree that e to the negative x squared is the same as 1 over e to the x squared? Okay, everybody agree with that? Would you agree that e to the negative x is equal to 1 over e to the x? Would you agree that e to the x squared is greater than e to the x? Right? Would you agree, and this is going to be kind of, not really abstract, but a third grade version of this. Would you agree that 4 is greater than 3? Yes. So what would be true about 1/4 and 1/3? Which one would be greater? 1/3. So 1 over e to the x is going to be greater than 1 over e to the x squared for every value of x. So if I can show that this converges, this is always going to be a smaller value than that. All right, let me pause for a second. All right, so now that I've shown that the output of either of these two functions, at best they'll be equal at 1, right, for x, and anywhere that x is greater than 1, 1 over e to the x will have a greater output than 1 over e to the x squared. Okay, so let's determine whether or not that converges or diverges. Because if this converges, it forces this to converge. What would happen if this diverges? What do we know about this? Well, let's look at a graphic real quick. Let's go 1 over e to the x, right? 1 over e to the x. Let's say it looks like this. Here's 1 over e to the x. Okay, and we know that 1 over e to the x squared is going to be less than that for all values of x and equal at 1. So I guess we could say that, right? Can we determine whether or not this will be convergent or divergent? If this is divergent. Can we say it diverges? Okay. Together. Okay, don't check out. All right, so if the upper function diverges, we cannot say convergent or divergent for the underside function, right? We can't. We can't say it diverges because the one above it diverges. If the lower one diverges and we know that, then the upper one for sure will diverge because it's always greater than. If the lower one converges, it tells us nothing about the upper one. If the upper one converges, it tells us everything about the lower one. So we want to find one that's greater, and we do. We have it, right? It's 1 over e to the x. Can we say that this converges from 1 to infinity? Let's find out. Because if it does, that tells us that this one also converges. So let's do it. 1 to infinity of 1 over e to the x. Now I don't want to integrate it in that form. I want to integrate it in the original form it was given. And I would use u sub. I would call u negative x, and du would be negative dx. So negative du would be dx, and then we roll from there. Okay, so u is negative x, so this would be e to the u. And dx is negative du, so I would bring that negative out here. So let's prove if this converges or diverges from 1 to infinity. So the integral of e to the u is e to the u from 1 to b, where I'm going to take the limit as b goes to infinity. So negative e to the, what is u? Negative x from 1 to b as b goes to infinity. That should be a little bit nicer. Okay, so what would be a nicer form to write this in? Because that's ugly. Negative 1 Yeah, negative 1 over e to the x power. So why is that great? Because as x goes to infinity, or as b gets plugged in and goes to infinity, that becomes 0, right? So I'm going to just write this all out for those that need it. Negative 1 over e to the b minus negative 1 over e to the 1. What would happen to b? Well, this would go to 0, and I'd get negative, or 0, minus negative 1 over e. So the area under this curve is finite. If it's finite, then that means it converges. Okay, so that means this function converges. Therefore, since the integral from 1 to infinity, I'm going to imply something here for a second. Hold on. Negative, what was the original function? Got lost there. There we go. E to the negative x dx converges, and the integral from 1, oops, I don't even need that. Let's do this. Since e to the negative x will always be greater than or equal to e to the negative x squared, that tells us that the integral from 1 to infinity of e to the negative x squared dx will also converge by what's called the comparison test. Okay, so we're going to pick g of x that are larger or smaller than f of x, depending on what's easiest to do for us. And sometimes you might end up doing both and trying it a couple times. So here, oh, that's gross, right? That's gross. But let's talk about this for a minute. When we talk denominators, if I have something bigger in the denominator, how would that be related to something that's got a smaller denominator? Which one's greater? The one with the smaller denominator, right? So I want to find something that's smaller than this. I want to find something that's smaller than that. Well, I could right away find something that's smaller than that, right? I could do this. How about this? Wouldn't that be smaller than that? Yeah. And wouldn't that be equal to that? So couldn't I use a comparison test with this? Almost. Almost anything. It's got to come directly from what we're working with, right? But all I did was I lopped off a 2x, and immediately that became smaller, right? Which makes the reciprocal of it larger. And the square root of x to the 4th is x squared. So, and what do I know about this? Is this convergent? I don't know the sum of its areas, right? But I do know it's convergent by what test? P-series. So P-series tells me that 1 over x to the p dx will be convergent if p is greater than 1. So since the integral of 1 to infinity of 1 over x squared dx converges, and 1 over x squared is always greater than or equal to 1 over the square root of x to the 4th plus 2x, that tells me that this one must also converge. Am I getting an answer for like what the area is? No, I'm not. That's not the point. The point is I just want to confirm whether it converges or diverges. And I proved it, it converges.